Hello everyone. In this video, I would like to continue with our previous lesson about related rate. We have worked with two examples already. Alright, so let me go back and review for everyone briefly what we have done. And then after that, I will go over this example with everyone. In previous video, we are talking about related rates and how all of these apply to our electronics problems. So if we solve for a related rate problem, we need to determine the equation if it's not given to us. We need to identify the variables and the rate. We differentiate both sides of the equation with respect to time. And then we substitute all given rates and given values into the equation. Then we solve for the unknown. We also have to note that we are going to use negative for decreasing and positive for increasing. And at the end, our answer should work out to be the same. The result will show increasing or decreasing by negative or positive result. Okay, so in working with the related rate problems, the most challenging part is the identifying the variables and the rate. In fact, determining the equation is one of the most difficult part. However, most of the time the equation will be given to us. And to identify the variables and the rates, I kind of give everyone a hint that if we are talking about the rates, then we have to think of this in terms of time. Time is the factor determine the rate. So to find the rate, then to recognize a variable or a number is given to us as a rate, then we have to think of that number as a differentiation in terms of time. So for example, this example here, you take a look at this number 0.3 given to you at degrees Celsius per second. So right away you realize that this one is the rate. Okay, so basically we are going to use all of this step in our next two example in this lesson, in this video. And we also follow all of the steps. We differentiate implicitly. And we make sure that we multiply by the variable that we need to multiply by, and we don't miss out any rate or any variables. And for some problem, we have to apply the quotient rule, and we have to realize which one is a fixed value and which one is a changing values, so that we can substitute it into the equations given to us. All right, so let me start with question number 3. And this question, I have this equation as a guide. Okay, so now the current I through a circuit with a resistance R, a battery whose voltage E and whose internal resistor R is given as current I equal to the voltage divided by the total resistance in this case. So now you realize that this formula follows or obeys the Ohm's law, right? I is equal to E divided by R. And we are taking into consideration the resistance R and the internal resistance as well. So in analyzing this, we are going to take a look at the numbers given to us. So the circuit has a variable resistor changing at the rate of this number. So you see here, ohms per minute. That means we are talking about derivative of R with respect to time. So I am going to circle this number, and I'm going to remind myself this one is dr over dt. And then what we have next is with a 2.95 volts battery. So this is the battery where you are not going to change this value, right? So this is the E, and which is the fixed value. So this one, I am going to identify it as E, and it's fixed. Okay, so you're not going to change this, right? So the changing factor in here is in fact this number. okay, this number, because you have a voltage that is set to be a 2.95 volts battery. So this number is fixed and is also representing E, which is the potential difference of the voltage because of the unit here indicated so. Okay, whose internal resistance is this value? So what is the internal resistance? Internal resistance is the little r. So this one is also my little r. So R equal to 0.45 ohms. Okay, so I'm talking about this battery, 2.95 volts battery, whose internal resistance is this. And this value is fixed, so therefore this value is also fixed. You have these values of the battery, that means the internal resistance will be equal to this. So this values is also a fixed values. So this one is also fixed. So what is the changing variables in this case? The changing one is this value, variable resistor R. So R is the changing values. Okay. So the change in your circuit in here depends very much on what resistor that you connected to it, right? Because you chose the voltage to be 2.95. The internal resistance goes with this voltage, so these two values are fixed. But this values here is a changing variable. Because if you take this resistor out and you put in like let's say a 15 ohms, then you are changing the current in this case. But you are not going to change the E and the internal resistance that goes with your battery. Okay, so having figured this out as which one is fixed and which one is changing, you can substitute the values into the equation. Okay, so before, I would like to write a note for everyone here. They are asking me for how fast is the current changing. So this one I have to find di over dt. So di over dt is equal to the question mark when my fixed value R equal to 9.00 ohms. Okay. I mean the changing value R is equal to 9.00 ohms. I should say that. Okay, so R is changing. Then E is equal to 2.95 volts. And given the internal resistance for that will be the little r is equal to 0.450 ohm. So this R is fixed. Okay, so changing value, this one is fixed values. I should complete my sentence here. Okay, so this one is fixed value. Alright, okay, so I will write my equation like this. I equal to 2.95 of fixed values. The changing value, I leave it as the variable. And then the fixed values again. Alright. Okay, so now I am going to differentiate this. I'm going to find di over dt as they are asking me to find. Alright, so in order for me to find this, I am going to convert this into r plus 0.45 and I raise this to exponent minus 1. So I raise this to exponent minus 1, then all I have to do is just applying the function raised to a power, apply chain rule when I'm differentiating, and I don't have to worry about the quotient rule in this case. Alright, so doing this, I will take minus 1, I multiply by 2.95. At the same time, I will take 1 away from the exponent, so that will give it negative 2. However, I differentiate this in terms of time as well, right? So I need to multiply by dr over dt. So you don't want to miss this dr over dt. Okay? Alright. So I realized that I kind of skip a step. I skip a step let me rewrite this because I do have a lot of time. So I am going to write this because I mentioned to everyone that we are going to differentiate implicitly. So in the end, I will rewrite the other line for everyone. The line that I just erased, they will just be the same, but I kind of want to emphasize this here. Exponent 1, this differentiate in terms of time, right? So I differentiate this, one side of the equation in terms of time, the other side of the equation in terms of time. So this one, I still have di over dt, and then I have this equal to 2.95 times minus 1 times r plus 0.45 raised to the negative 2, and then I multiply by dr over dt. Okay, so now I am going to substitute r equal to 9, okay, into this equation, and I am going to substitute the dr over dt, which is given to me as 0.0597 ohms per minute, to figure out di over dt. So di over dt will be equal to 2.95 times minus 1 times 9 plus 0.45, all of it in the brackets, raised to exponent negative 2, multiplied by 0.0597. And if you use your calculator, which I believe everyone is a master of that Casio FX 991 MS calculator at this point, so we should have negative 0.001972 amps per minute. And I need to round this to 3 significant digits. Okay, so then I should express it in engineering notation as well. So you are going to move the decimal point here. So I should have 1.97 negative milliamps per minute. Alright, so this one, 3 significant digits, and also in engineering notation. Alright, so I strongly recommend everyone to make sure that you use your calculator, key this into your calculator, and then make sure that you get this number. Alright, okay, so let's recap what we have done for this example. For this example, basically, you see there's a changing variable in here, dr dt. Okay, so if you take a look at this unit, you figure out this variable, and knowing that this has to be the changing variable anyway, right? So then E is a fixed value because you pick that battery, and inside this battery you have an internal resistance. So this one is a fixed value, this one has to be a fixed value as well. So then you substitute that into your equation, and leaving the r, because r is a changing variable, so you have to differentiate this r, and then you have to find di over dt. So if you translate this whole sentence into mathematics, then it's just what is how fast the current is changing when the resistance of the variable resistor is equal to 9. And 9 is a changing value, E equal to 2.95. The internal resistance that goes with this E is equal to 0.450, so ohm, so it's also the fixed value. So differentiate this implicitly, and because we differentiate everything in terms of time, so we need to multiply by dr over dt, and the value is given to us here. Then in the end, this is the answer that we have. Alright, and we will put our answer in 3 significant digits and also in engineering notation. The reason we put 3 significant digits because all the values here given to us in 3 significant digits. Alright, so let's move on to the next example. This example, I am talking about the related rates with more than 2 changing variables. So this poses a bit of the challenge here. So we have to find how fast the power in the circuit changes. So when we are talking about how fast the power, that means I somehow have to know that okay, so I'm going to write this down. How fast the power changes. So in this case, is in fact is the derivative of power as a function of time. Okay, so we translate this into mathematics right away. When the current is equal to 9 amps. Okay, so when the current is equal to 9 amps, so that means this is representing I. Okay, so this is representing the I. And decrease at the rate of this. Okay, the rate decrease at this rate, so that means it's di over dt is equal to negative 0.5. Okay, so I will write this down. Decreases at the rate of 0.5 amp per second. So the key here is, okay, so I should put I decreases. So the key here is this one. I should write di over dt equal to negative 0.5 amp per second. Alright, okay. So, and the resistance is equal to 50 ohms. So if we talk about the resistance equal to 50 ohm, so here we should have R. So let me leave some space here. So R equal to 50 ohms increases at the rate of 3.5 ohms per second. Okay, so in this case, I have another changing variable here. The R increases at the rate of 3.5 ohm per second. So we are talking about dr as a function of time and differentiating R with respect to time. So then I should have 3.5 and ohms per second. Okay, so I'm going to give myself some room and I rewrite this. So this one is dr over dt at increase, so I should have positive 3.5 ohm per second. Okay, so we analyze our problems, and we try to read all of these variables, the rate, and how are we going to find the power in this case. And the equation is not given to us. Okay, so the equations for the power that's involving your I and your R is actually this formulas right here, which I kind of given it to everyone in previous handout. In the previous lesson, I mentioned about this. Okay, so if you want to find the power given the resistor and the current, or the resistance and the current, then this is the formula that you are going to use. So the I here representing the instantaneous current, and it's representing the change, the rate that we are talking about in this particular problems. Okay, so let me write this for everyone. Okay, so I'm going to summarize this in the sentence for everyone. So it say that I is equal to 9 amps. Okay, changing at the value at the according to time. Okay, so here negative 0.5 ampere per second, and then I have R equal to 50 ohms, and this one is also changing according to the time. So dr over dt is equal to plus 3.5 ohm per second. Okay, so we are having quite a few changing values. So this is the two changing variable in this case. Okay, so we have this, we have that, we have that, and then we have that. Then what do they ask us to find? They are asking us to find the derivative of power as a function of time, because they're asking us to find how fast the power in the circuit changes. So working with this equation right here, okay, I am going to write it down. P equal to Ri squared. So you probably ask me this question next. Okay, you asking me this question. So in previous lesson, I kind of show everyone to put in the fixed value and then leave the changing value alone, because you are going to differentiate according to the changing variables, right? But in this one, all of these are changing. R is also changing, I is also changing. Then don't worry about it. You are going to differentiate these formulas according to what you need to do, like with respect to time. So differentiate implicitly both sides of the equation with respect to time, and then all of this variable you are going to substitute them in, because there's no fixed value here for you to substitute in, because they are changing. I is changing and R is also changing as well. So this problem have two changing variables. So if I work with this, I know that I have to work with product rule. Okay, so to work with product rule, let's write that down. So product rule, I should have U times dV over dt plus V times du over dt, because I'm working with the variable t at this point, right? And then I am going to ask you to differentiate both sides implicitly. All right, okay. So now this is the product rule that I'm talking about. This whole thing here is the product. That means I am going to identify U as R. Okay, so if I identify U as R, then du over dt will be equal to dr over dt. All right, okay. So if I identify V as I squared, all right, okay, then dV over dt is 2 times I raised to exponent 1 and multiplied by di over dt. Okay, don't underestimate the power of writing derivative of p as a function of t, like with respect to t, derivative of this product with respect to t, because this dt is very important in terms of if you differentiate this I, okay, with respect to t, you have to multiply that by di over dt because of the chain rule. Alright, so we have everything we need, right? We have the u, we have the dv over dt, we have the v, and we have du over dt. So now what we have to do is substitute it into the equation. So we have derivative of power as a function of time. Then I should write it as r. Okay, so this is my u. So this is u. And I multiply that with dv over dt. So that means I multiply by 2i times di over dt. So this is my dv over dt. And then I add that with I squared times dr over dt. And I squared is v, and this is my du over dt, the exact match of what I had to substitute in for my product rule. Now at this point, you just substitute in the value that given to you, and then you are solving for power, how fast the power changing. So R is given to me as 50, right? 50 times 2 times I. I is given to me as 9. So, and then di over dt is given to me as negative 0.5. And then the I here will be 9 squared. And dr over dt is given as 3.5. Okay, so all of these values are given to me up here. As you see, we identify them all up here. I, R, di over dt, dr over dt, which we have them all taken care of. So the I, the dr over dt, the I square, dr over dt, and this is di over dt as the negative. So working with this, I am having this equal to negative 166.5. What is the unit for power? Which is watt. And then the unit here should be in second. It's because up here they are giving me the amperes in terms of second, and also the ohms in terms of second as well. So I have this as a second here. Alright, and this one is also a second. So the final unit for this should be watts per second. And I need to round this to 3 significant digits. Okay, so in 3 significant digits, I should have negative 167 watts per second as a 3 significant digit. Okay, so I have a few minutes left. I am going to quickly recap this question for everyone. Alright, so basically what you need to do is you need to translate this word problem into the mathematics. So how fast is the power in the circuit changing? So immediately you identify that as the differentiate the power in terms of time. So derivative P as a function of times. Whenever we talk about the rate, it's related to a differentiation here. When the current equal to 9, so I can put the I for this current because it's the it doesn't say anything about the rate here. And now it's at decreases at the rate of. So when it's at decreasing at the rate of, I will identify this one as di over dt equal to negative 0.5 amps per second because it's decreasing. And the resistance is 50 ohms and increases at the rate of 3.5 ohms per second. So this one increases, so I need to have the derivative of R as a function of time. Increases, so I need to have the positive value in this case. So now you see you have two changing variables. You have the variable of the current and the resistor, and they both changing because they give us the increases and the decreases in this case. Then you just have to list them down, and then they're asking us for the how fast is the power. So we are going to search into all the formulas that we have learned. According to Ohm's law, if you are given R and I, to find power, it will be P equal to R times I squared. Okay, so we use these formulas to figure out our derivative of P as a function of time. This is the unknown that they ask us to do. So we are not going to substitute any values into here because we don't have the fixed value to substitute. So we just have to differentiate this equation and differentiate this equation in terms of time. So when we write this down, we see that I have the variable R, I have the variable I. They are two different variables and they multiply with each other, so I have to use the product rule. The product rule indicated this. I identify U and V and I follow these formulas. So then I will let U equal to the very first variable that I see, which is R. Differentiate this in terms of time. So du over dt is equal to dr over dt. And here as well. And then substitute the value in to solve for it accordingly. At the end, you know that all the variables and the rates that you identify will substitute into your differential equation and you solve for the final values. Okay, thank you everyone.